Donc Federico est maître de conférence à l'université de Rome, l'université Sapienza. Et donc c'est un chimiométricien qui fait partie du paysage chimiométrique européen, hein, et voire peut-être même mondial. Ça fait un certain nombre d'années qu'il est parmi nous et qui nous présente à chaque fois des travaux relativement intéressants. Donc il est du domaine, donc il a beaucoup travaillé sur les méthodes type ASCA et associé ou non à tout ce qui est plan d'expérience. Et aujourd'hui, il va nous présenter une synthèse, un petit peu une synthèse générale sur les stratégies chimiométriques pour l'analyse multivariée des données provenant des plans d'expérience. Et donc, on va retrouver au cours de cette présentation un certain nombre de techniques et de méthodes autour des plans d'expérience. Et donc, j'espère que ça va bien démarrer la journée. Donc, Federico, à toi, 40 minutes. Je récupère ça.
Oui, merci pour cette introduction. Il est vraiment un plaisir pour moi d'être ici. Et je voudrais remercier le comité organisateur et le groupe français de chimiométrie pour m'inviter. Mais je suis en anglais pour la conférence. So, the idea behind the talk is to try to make a general framework and to highlight like the strategies that have been proposed in the literature to address problems that are increasingly growing, where a set of multivariate data is collected from experiments that are planned according to an experimental design. And of course, the idea to have suitable instrument to analyze data coming from an experimental design is nothing new at all. Already in the first edition of his seminal book, that is The Design of Experiment, Rolf Fischer was pointing out that, of course, try to extract meaningful information about system without a carefully designed experiment is meaningless, but is also, let's say, a sort of underuse of the models to try to model the results from the data without taking into consideration directly the underlying experimental design. So that, of course, a suitable statistical procedure and coupled to a proper experimental design should be considered as the two sides of the same coin. And the idea, of course, between the experiments that are planned according to an experimental design is to vary in a controlled fashion one or more factors in order to evaluate their effect on one, but in our case, possible multiple responses. And the idea, or the things, the information that we would like to extract, of course, as it was already pointed out yesterday in a couple of talks that were showing some application of the same concept, already anticipating, let's say, I would say, the introduction and the meaning of this talk, would be to try to extract this information that should be, okay, can I measure an effect that is significant? So can I say that that particular factor or some interaction between the factor is significantly causing a variation in my response that I cannot ascribe to random variability? And on the other hand, of course, especially in the case of multivariate data, like our idea would be to try to interpret as simply and straightforwardly as possible the effect that we see or whose significance we assess in a way that we can take, let's say, information out of it. And the basic of all, like the approaches that have been proposed in the last years for the analysis of multivariate designed experiments or multivariate data coming from design experiments all start from the general and classical concept of the analysis of variance, or if one would put it in a more general fashion of the linear model. So where one assumes an additivity of the individual contribution, so that if I can assume to have two factors, of course the response, in this case univariate response that I'm measuring for the kth replicate of the variable that I was acquiring with factor 1 is at level I and factor 2 is at level j, can be considered as the sum of an overall offset or a grand mean term, a contribution, average contribution for factor 1 being at level I, and average contribution of factor B and level j, and their interaction, and some residual that, of course, I can only measure or evaluate if I am collecting more than one replicate for each unit of the design. And if we look at it, of course, the main concept behind the linear model is that even for a simple univariate case, this partition of the effect is ambiguous, and it admits, of course, multiple solutions that are equally valid just by introduction of offsets and additional multiplicative terms, so that, of course, I need some constraint to get unicity of the solution. And the one that is always, well, most commonly used is the sum to zero constraint that is so standardly used that is called the usual constraint in this framework. And under this constraint, we can just decompose our response into the individual contribution, calculate the least squares estimate for the terms alpha, beta, and so on. And then we just need the last part for the univariate case, that is assessing whether this effect is significant or not. That is usually done in a classical framework by means of an F-test. But what does it happen when we go towards the multivariate situation? Of course, is that we can still think that we can apply the same kind of multivariate decomposition, analysis of variance, ANOVA decomposition, to a data matrix. In this case, I have multiple samples, but also, more importantly, I have multiple variables that are collected at each replicate of the different design unit. So the idea would be, once I have subtracted the general offset, so once I have the centered matrix, to be able to decompose or to the overall variation into contribution of individual terms plus a residual matrix which accounts for the variability not ascribable to the control factor and interaction. And how I'm normally doing, I'm just generalizing under the usual constraint the same calculation that I was showing before for the individual variables of the matrix. So for instance, if I have only 2 levels for factor A, 2 levels for factor B, that means I have also 2 levels for the interactions, then what I would end up is that, for instance, the factor A would be represented by a multivariate matrix being only made of 2 signals, that is, replicates of the mean profile for the samples that were collected at level +1 of the factor, and replicates of the mean profile for the samples that were collected at level -1 of that factor, under the constraint of sum to 0. That means that these profiles would be centered. And the same holds for factor B, for factor AB, for interaction AB, and of course the residual terms is just obtained by subtraction, because it's all the variability that is not accounted for in this situation. And this could be seen, for instance, in a case, these are spectroscopic data that we're collecting according to a 4 to the second, so a full factorial design involving 2 levels for factor 1 and 4 levels for factor B. These are coffee samples from different variety and roasted for different times. And you see that the overall profile can then be described as the sum of an offset term, that's the mean spectrum over the samples, a center matrix accounting for the variability ascribable to the variety, to the roasting time, to their interaction, and the residuals just comes out as the difference between all these contributions for the different sample. And that is quite important, because sometimes, especially in order to get an overall picture of what all the methods available in the literature would do, we miss the consideration that if we want to think classically, and we will see it here, in terms of the classical tools for analyzing multivariate design data, that is the multivariate analysis of variance. All the different techniques that have been proposed in the literature, or at least most of them, actually give a same estimate of the between levels of the factor contribution. So let's say what is considered to be the inter-level variability for each factor is estimated with the same kind of scheme for all the methods that, or for most of, or almost all the methods that have been proposed in the literature. And what is different is actually the second part, so how the significance of the different effect is tested, and also later on, if significance is observed, how it is interpreted. So the standard way of addressing, based on this decomposition of addressing the significance of the effect, would be the standard, the classical multivariate analysis of variance. Here, the same consideration for extracting the matrices is reported in, in the framework or expressed as a regression model. But the idea is still to have, let's say, a multivariate matrix accounting for the mean effect of factor A, mean effect of factor B, their interaction, and some residual variation. From a classical standpoint, the assumption is that, let's say, the dispersion or the within-level variance for the different terms is the same across all the design. And with this assumption, then one can do testing in several different ways. One way is to calculate Wilks lambda. There are other, of course, ways of doing so. And in this case, one can test whether the individual effect is significant by transforming variation into between and within matrices of sum of squares and cross product. The thing of that is that with our data, so with our multivariate data, we know that, of course, this is not doable because the matrices are not invertible and in conditions, so we need to find alternatives. And some of the alternatives actually have been cited yesterday. I will try to sketch within the same framework, well, many of the possibilities, not all of them. In the last slides, there are also some, let's say, reference to additional methods that have not been treated in the present communication. But the first way of addressing this problem was to use what is called an ANOVA-PCA approach. In the framework of ANOVA-PCA, then one starts always from the same decomposition that it was shown before. So centered data are decomposed into a sum of different effect and interaction matrices plus the residual. And then, let's say, for addressing the effect significance and for interpretation, what one does is to take the individual factor matrix and adding to each of the factor matrix or the interaction matrices the residual matrix. So one obtains something like that, taking the same data that's shown before. For instance, this is the two-level matrix for factor 1. Then I am adding on top of that the residual matrix, and I obtain this matrix that is then subjected to PCA. And the same for the second factor. I take this matrix and I do PCA, and the interaction, I take this matrix, I sum them and do PCA. And this is what I obtain, and the idea would be that the first principal components, depending on the amount of, well, on the level of the factor, but the first principal components should account for the between level variation. So in this case, we see it more or less, that the first principal component differentiates between level 1 and level 2, or if we want to see it, -1 and +1 of the factor. And the second, or the remaining principal components, should account for the residual variability. And testing is not done in a very, let's say, in a statistically rigorous fashion, but just by comparing like the variance explained by the different components. Interpretation, of course, is done by just inspecting the loading of the matrices. Based on the same concept, there was something proposed by Finn, Douglas, and others about the method that is called ANOVA Konjam, that is based, as the name suggests, on the common component and specific weight analysis method, by taking into account the same kind of use of the factor matrices and residual matrices. So one starts always by the matrix obtained by summing up the factor and the residuals, and puts these individual matrices under a multi-block context by the use of Konjam. And the idea, of course, is that the common element among the matrices, including the single residual matrix, is just the residuals. The idea is that the first components should be mainly associated to noise and the other one to the different effects of factors and interaction. So by comparing the saliencies, one could have an estimate of the factor significance, and then, of course, proceed with the interpretation and so on. But the method that is probably gaining more popularity in the literature is the so-called ANOVA simultaneous component analysis, which is ASCA, that was proposed by the group of Ashmilde, more or less at the same time as ANOVA-PCA. The decomposition is, of course, the same, but in this case, the idea is that the individual factor matrices are first analyzed and tested independently without taking into consideration the residuals. So if we look at that, the idea is that we need something to estimate the effect entity or the effect magnitude, and this, consider that these matrices are centered, is made by taking into account the sum of squares of the matrix element as a measure of how the factor variation induces a variability in the multivariate profiles registered. So one transforms this matrix into a sum of squares, and by accounting or calculating this sum of squares, then try to estimate the magnitude of the effect. But then, of course, we need something for testing. And testing can be done, well, let's say classically, or in a first approach. Testing was proposed to be done using permutation test. Permutation test has the advantage of being non-parametric, so it can be generally used, let's say, sort of assumption-free. But of course, they have the inconvenience that one can build in the framework of this kind of situation, one can build an exact permutation test only for the main effects. And indeed, when one wants to try and test the interactions, well, one can obtain severely different results depending on the way the interactions are tested. In general, let's say, it is suggested in a paper that was also cited yesterday in one of the talks, that the best approach for doing this would be the permutation of the residuals under the reduced ANOVA model. That is something that could be equivalent to sort of type 3 sum of squares. The idea, of course, of permutation test is that what I'm doing is just I am disentangling the factor labels, so that, for instance, I'm not considering here that this sample is actually coming from level -1, and this sample is coming from level +1, but I'm just scrambling their labels and then calculating the matrix, the effect matrix under the permutation, and of course I'm calculating also the corresponding sum of squares in order to have an empirical distribution of the effect under the null hypothesis. And by comparing the sum of squares of the of the experimentally observed effect with the distribution under the null hypothesis, I can have an estimate of the significance of that particular effect for factors or interactions. On the other hand, interpretation is quite straightforward, because since I am just considering matrices containing the mean level, the mean profiles for the different factor levels, for instance, in this case, I would have only 2 points in the score plot if I do PCA or SCA. That's more or less the same in this context. So then I can easily see what would be, let's say, the variation by comparing the scores observed with the loadings. In this case, of course, I can have a first other way of assessing in a more graphical way whether an effect is significant or not, because on top of this PCA model or SCA model, I can back project the residuals, so I would obtain not only the average, let's say, point or coordinate for the mean factor signal, but also a distribution or an idea about what should be the scatter of the data around this, this factor level. So a sort of within level variability that is actually graphically projected. This is the same data showed before, so the coffee data. And this is an example of what I could see. I can get by having first just the two scores, so -1 or minus something and plus something, and the scores with projected residual for the first effect, that is the coffee variety, Arabica and Robusta. I can also take this and express it under the form of an histogram just for the sake of visualization, and loadings that actually are also accompanied with a bootstrapped confidence interval for the interpretation of the effect. And this is the effect of roasting time. It's not very easy to see it with this projector, but we have, let's say, time 0, intermediate time, and the two end times that are almost giving the same results in terms of the profile, telling that probably, let's say, 50 minutes of roasting is enough, because after 75 I got more or less indistinguishable effect. Similarly, another method that was proposed by myself, Beata Walczak, and people from South Africa is called ANOVA-target projection. That can be considered, or let's say abbreviated as ANOVA-TP. The idea is always the same, but in this case the idea was to try to use not an exploratory technique for build the model, but a regression technique, namely PLS, to try to build a model between the design matrices and the experimental matrices, and use, of course, this model for further interpretation and testing. In this case, what we found is that a better and a better model in terms of accounting, in a relatively accurate way for the within variance, that is actually one sort of drawback of the previous approach shown with ASCA, that when one back projects the residual matrix onto the SCA models, what one ends up with is that normally is overestimating the effect of the residual variability, also compared with the significance of the effect that is observed. So we try to get a better description of the within level variability, so that means also a better or a more accurate testing for the effect, by trying to use PLS and then further target projection for interpretation in this framework. And what we found is that actually a better way of building each individual PLS model between the data, so the measured profiles, and the design matrices in order to check for the effect of interaction, is not to start directly with the centered data, but to use what is called the residual matrix after the reduced model. So it's something that was similar to the same matrix that was used in permutation testing for interactions in ASCA. So the idea is to take the centered matrix and remove terms that do not account for the variation to be tested. There are different ways of trying to see which effects or which terms should be kept, and the same approach should be in principle valid for different kind of design, even if so far we only tested it on cross design with fixed and also with random effect. And these are so-called assay diagrams that I don't have time to go in detail into, but this is a nice way of representing the main terms and the interactions in all kinds of design, and can guide us, first of all, to decide which effect is fixed, randoms, and so on, and also which terms one should remove depending on the design, in order to build the matrix to start with. So once we have this matrix, we just calculate a PLS model taking as Y the design matrix. And then if we want to have interpretation, that means if we want just to condensate the variation onto a minimum number of PLS component, that is something similar to what we would obtain with ASCA, because of course with ASCA, if we have only 2 levels, we would obtain a single principal component accounting for 100% of variance, is to use what is called the target projection. A target projection just means that the PLS subspace is projected or rotated towards the regression coefficient, or the regression coefficients if one has a multiple Y, in order to get meaningful directions. And one gets a set of target projection scores and loadings that can use for interpretation. In this case, of course, we have already, differently than what happens with ASCA, we have already the within-level variability associated with this target projection solution. And what we found is also that in the case of a balanced design, then if one just takes the average target projected scores for the different level, one ends up with an estimate that is very close to the ASCA estimate. The only difference being that the within-level variability is better estimated, or is, let's say, gives a smaller variation. In this case, one can test by permutation the residual of the predicted Y, or the reconstruction, as it was done in ASCA as well, of the target projected estimate of the X matrix. That it can be obtained just by multiplying target projection scores and loadings. And this is what I was saying before. If we compare for the same problem, this is a production of green tea, different kind of fermentations for South African green tea, one sees that the estimate of the within-level variability is different, whereas the mean, so the between-level variability, is more or less estimated in the same way. I have probably some minutes more. So what I would like to show is just coming back to ASCA, something that has been recently proposed, so the paper is just an early view on Journal of Chemometrics about the possibilities of using multivariate regression theory to get a different way of estimating significance and do testing in the context of ASCA. So the idea would be to start by expressing let's say, the multivariate ANOVA in the regression framework as it was shown some slides ago. And then it is possible to show that according to the theory of multivariate multiple regression, one could in principle build ellipsoid or confidence ellipsoid around the least squares mean for the different levels and combination of levels depending on what ones want, according to this formula. And this holds, of course, for the general linear model, so including all the terms, but also for the individual effects. So one could do the same estimate, first of all, by taking into account the individual least square mean for the individual mean for one particular level in one particular factor of interaction. And by using or propagating the contribution of the loadings, one can also, let's say, take into account the ellipsoid that would be built when this least squares average would be projected in a reduced space, for instance, using PCA as it is done in ASCA. So that would give us some confidence ellipsoids that are something like this. So this is what would be, let's say, the variability that one would obtain around the mean factor levels when using the back projection of the residuals onto an ASCA model. And this would be the estimate of the uncertainty or the confidence associated to the general linear model after the projection onto the reduced space, according to the theory that was proposed in this paper. And this is for another example, so for another factor considered for this example. You see, this is what we would call a data ellipsoid, so that would be just taking into account the variability after projection of the residuals, and these are the variability or the ellipsoid 95% ascribable directly to the ASCA model according to the theory. And the good thing about that is that one could also consider difference between levels, so to do, let's say, a multiple testing or pairwise comparison by using the same framework, and this is for the same example as here, where the testing between the difference between the individual assessor was tested according to this framework. And that's it. So I think that I hope that I was showing, let's say, a general framework for different methods that have been proposed in the literature, recent literature, to assess multivariate data coming from design experiment. This was, let's say, the idea is that the important things that should be addressed, whichever method one wants to consider or to propose, is of course like how to do testing, how to evaluate the factor effect, how to do testing for this factor-effector interaction, and how to do interpretation. Due to the time, of course, the proposal was not exhaustive. There are methods that have been left out. That was, for instance, the recently proposed regularized MANOVA or the ANOVA multi-block orthogonal PLS, and others that are not also considered. So I think that's it, and I thank you for your attention.
Thank you, Federico, for this talk. Nice talk. Alors, des questions? Est-ce que vous êtes un peu réveillés sur ce sujet? Non. Gilbert, c'est bien.
Ladies first.
Yeah. So thank you very much for your nice talk. I am, of course, interested by your last paper. I didn't read it. So could you explain me what is the matrix sigma? So it's the matrix sigma on the correlation of variance covariance matrix of the residuals?
Yes.
And if yes, how do you estimate it and invert it? Because it's a very big matrix, and that's really the problem in these models. So I don't know how you solve that.
So we were solving by Cholesky.
By what?
By Cholesky decomposition.
Okay. Okay, so I would try to think of that. So thank you. But I think it's a very nice idea to work on the contrast directly. I think that's the solution in these models. To ask the question and translate them in contrast, and then you get the results.
I would say that it took about 1 year to figure out how to properly calculate the sigma, because it was also more or less most of the things were there. So in how to estimate probably in a reasonable way that thing.
And how do you calculate the degrees of freedom with the rank of the matrix, or? Because there you should take in account the rank of the matrix. Or
yeah, I mean, we did this estimate here. So
yeah, I see that there is a number there, but yeah.
Yeah.
Okay, so it's a very nice result. I will try to study it.
And I think that of course could be like very useful to couple what your group was proposing with this approach.
But it's an extension to mixed models, so I think there are a relation between those results.
Okay, Federico, it was a very nice talk. Thank you very much. I have a question about the case, which is not so infrequent, where the observations are not independent. For instance, when you analyze the spectrums, you have a strong autocorrelation, which is sometimes by design. How do you take this into account in your methodology?
Well, it's not my methodology, but I mean,
yeah.
I'm just was surveying at least some of the things. And Well, what I would say is that, of course, you can try to take, especially in the last approach, or in this approach with ellipsoid, you can try to account for this, but it's not straightforward. And in the other approaches, what you do is normally taking into account implicitly, because, for instance, like you take into account the correlation between variables in ASCA when you're doing the testing. So within the permutation, it's sort of implicitly accounted for. In the other approaches, of course, that are based on previous PCA, you take it into account before. So the different ways actually the methods are differing. It's just about this and how they addressed the correlation between the variables in the moment of testing. Because of course, like the mean values or the mean factor levels are there. And of course, the different way you take into account correlation in the residual or in the variation gives you how you test for significance. But all of this is normally doing an implicit way differently for the different models.
I come one more with a question. So I didn't understand directly the L matrix. So, excuse me, it's a technical question, but when do you calculate the loading matrix? Before doing the decomposition? It's the loading matrix of the initial?
No, it's the loading matrix it's the loading matrix of ASCA. So it's the loading matrix for projection, for projecting the effect matrix onto the reduced subspace.
So it's the loading matrix made linked to one effect?
Yes, yes.
So for each effect, you have a loading effect,
yes.
It's not the general loading matrix?
No.
Because what Manon is doing is that she do the projection beforehand. So I was thinking...
One should see, I mean, the thing is that, of course, due to the SCA, let's say, constraint, the loading subspaces are orthogonal. So probably you would get, well, at least for balance, the problem comes with the unbalanced design. So, but for the balanced case, I think you should get the same results, because for the balanced case, the loading subspaces are orthogonal. So if you get, and the design matrices are orthogonal. So when you're just projecting, then you should do it. I think I'm not sure about what to expect for the more interesting cases. So when you have unbalancedness.
Okay, thank you.
Interesting presentation. Two questions, mainly because I'm not sure I've actually understood all the details. In the case of ASCA, isn't the loadings vector just the difference between, if it's a two-level case, the difference between the two averages?
Oh yes, if you have only two levels, yes.
Yeah. So in fact, there's no need to do a PCA. You just calculate the difference between the two means and use that as the
thing is different when you have more than two levels.
Yeah, true. And what do you see as the advantage of ASCA compared to APCA? Because it's true, everybody uses ASCA, hardly anybody uses APCA.
Well, yes, I think that you get, in a relatively simple case, you got almost the same result. So if you see them, I show you. This is a relative, I would say, simple case, but already you see it. So if you consider that, so there's quite a high, especially take the main effect, do not take the residual, the interaction. But for the main effect, these are quite well separated, so, and quite significant. So you see that the division that you would see in ANOVA-PCA, especially for the variety effect. In the time effect, you get things that are a little messier, that when you do ASCA. So the thing is that is the disentanglement between the factor variabilities and the residuals is generally clearer, more evident in ASCA, at least from an exploratory data fashion, I would say. But
that's because you haven't included the residuals.
Especially when the significance of the effect is not that large. So in this case, like separation was quite good, so you could probably you would have seen it in this example that I was taking for as an exemplification, at least for the effect of variety, you would have seen it even between the standard PCA on all the data. But,
Okay, thanks.
Merci.